How's that? There? Is that good? Is that good size there?
Yeah.
Okay. Thank you. All right, so we're gonna execute this. One of the things I think everybody here has a question about where sites are. This is another tool the database can use for. It's just figuring out what's available, and not all NSIC data is on there, but it's happening slowly. But here we can go. We wanted to see the unique sites from our sites table, and we'll elaborate more on what tables and how it's structured in a little bit. And we're going to execute that query, and then we're going to just print it out in kind of a fancy way. And right away, you have all the site identifiers for all of the SnowEx data that's in the database, which in this case is just the time series data and the IP data. So you can do you can do some SQL operations here like this, and live in Python space, and never deal with what we're about to go into. But I'm going to try to convince you this is the way to do it. We are going to focus with the session object, which allows you to do all of these things without knowing SQL. Hopefully it makes you excited. Made me excited when I saw that it exists. And this is going to use something called object relational mapping. And I'm super pumped that we got Romina showed us about object-oriented programming, because it's very relevant to what we're about to talk about. And the only reason I use this term ORM is because it's super useful for Googling. But what it is at its core is we're mapping the tables in the database to a Python class. So every column is then got an attribute in the class. So we have a site ID for each table, and then all the other columns that exist there. And each row then is represented by this class. We'll go into a little bit. But if we wanted to execute the same query that's up here in this kind of weird object relational mapping form, this is what it would look like. From SnowEx SQL.data, we're going to import this table reflection called site data. We're going to build this query and say, I want the distinct version of all the site IDs. And then I'm going to execute that query and get some results back. And then again, we'll print and we'll close out our session. Execute that. And again, you see it's the same thing, but we didn't do any SQL. So that's really cool. Is anybody having issues right now doing these blocks? Nice. That's a really good sign. That's what happens when prime time happens. Things get better. Okay, so let's talk a little bit more about the object relational mapping. Let's suggest for a moment we have a small table that kind of looks like this, where we have an ID and a site ID and maybe some other attribute like round reference, which is an actual column in the site ID table, the site data table. If we were to see this in some kind of table visualizer, this is maybe what it would look like. In Python land, how this is getting mapped is each one of these rows is being matched to our site data class. So this row now has a site data.id that matches this first row and site ID and so forth, round reference, right? When we ask for site ID stuff, what we get back are these really ugly objects of memory. And when you see them in the list, it's kind of annoying. You're like, well, I don't, that's not very cool. But what's cool is now you have all these objects, we can go and get at some of the data. And so if you were to say print my query data and the first thing in the list, and you said dot round roughness, you would get rough, right? And that ends up being what was in our table up here. This is probably, in my opinion, maybe the biggest barrier to what we're doing with the database. And so don't feel bad if this is like kind of blowing your mind a little bit, or it's really hard to grapple with. This was hard for me to get, and so it's just, to me, it's the technical debt you got to take on to get not having to parse their data and all these files. So we just kind of covered a lot, but the highlights here is that there's this geo database that we can access in pure Python. And to do that, you got to use SnowEx SQL, which is a library we wrote. It's pip installable. We pulled all the unique site IDs that are in the database. And then we had this kind of really high level introduction to what's called ORM, object relational mapping. Are there any questions about this stuff? Go.
So does the database lives on a virtual machine somewhere? Where is like all this stored? That they're just accessing through this script?
Yeah. So
you're like paying for to have
Right, yeah, that's a good point. PHP is paying to have this hosted on the AWS instance in the cloud. And we just have a PostgreSQL database running there. And then we open it up to the whole world for this event. In the future, we'll ask you to send your preferred IP addresses while we figure out what we're going to do on. But that's a good question. Yeah. Are there any other questions? What is ORM? Cool. Does the ORM make sense? Give me some head nods. Does the ORM make sense in terms of the object-oriented programs you just watched? There's these attributes, and we're trying to map into something that we're going to use, and these tables have these columns, which we now call it. Yeah, cool. All right. We're going to jump to the next one. So the next one is this number 2 here, database. Double click that, get in. So we're going to talk a little bit about how we organize the database, which may not be super intuitive, but I think when you see the strategy, you'll see what we're aiming for. What we're going to do is we're going to access the database. We're going to try to see what the underlying tables are and what matters to you guys. We're going to query those tables and try to see what columns are available and start to begin to form a picture of how you're going to attack the data that's in here. So to begin with, right here, we're going to execute this. We're just getting that accessor function, and we're going to create the string for the database. When you execute that, not a whole lot's going to happen. But when we go to the next block, we're going to get our session and our engine object, and then we're going to use the engine object to just see what tables are available. And then we're going to quickly close the session just to keep everything limited. And right away, you can see there's 5 tables. And there's one in here called spatial reference system. That's not a table we build or maintain. That's totally automatic under the system under the hood. And that's putting in all the projection information and mappings and all that. But you don't need to worry about that at all. Unless it goes away, then that means the database is broken. But the others, the points, the layers, the sites, and the images, these are the tables that we've built to host all SnowEx data. And we can import those from our data submodule in SnowEx SQL by point data, layer data, image data, and site data. And again, these are those ORM reflections of these tables, right? So if you execute these, see that, we're going to import these. Now, the biggest thing is, okay, well, I know there's data, I know it's in a box, and I'm just trying to figure out how to get at it, but what's in it, right? So we can use the reflection class and get the table attributes or columns, and then see what's in there. When we execute that, we'll print it out really nicely, and these are all the things you can do: dot date access, dot using elevation equipment, to use instrument, the value that's being stored there. So what I encourage you to do right now is right here, switch this table name out for one of the tables we imported right here. So maybe you pick layer data, right? And then just re-execute so you can see or site data or whatever. Just try one of those, see if it does what you think it's going to do. Hopefully nobody has errors. I get a little nervous when all my technology starts to stack up and it's got to perform in certain short periods of time. So if you look, you'll see that there are some similarities in these tables, and there are some things that are pretty different. Some of these lists are longer and shorter, and the question is, why? So we have a ton of documentation on SnowEx SQL's read the docs, which is just a link you can get here. But for talking's sake, we'll talk about what these tables form. So we call the points table any data that can be represented with a single point and a single value. So you can think of an example of that would be like manual measured depths, right? Each one of those has a lat long and one value associated. GPR falls into that same category, right? It's just kind of doing little breadcrumbs as it walks around, as Kate's getting his exercise in for the day. Kind of put some other examples. I think those are the ones. GPR. The layers data table is a little less intuitive, but it's any data that could be represented by a single point and a single value with a single vertical depth in the snow. So you can think of that as density profiles, and those density profiles get broken up into rows that then go into the database. So you can actually query by a distance in the snow if you want it, and only pull out right at center or whatever. Hand hardens profiles, any of that kind of layered data stuff that we get. That's why we call it the layers table. S&P profiles go in that way. There's a really cool example on Read the Docs where I use the S&P profiles and I highlight all of the profiles that were near pits that had brothel mentioned in the comments. And it really shows off the kind of cross data set query business, using the site nodes and finding S&P profiles and then using this depth component of that. The second to last one here is images, which is just where we're keeping the raster data. And there's not a whole lot to it. We have the rasters are all broken up into tiles, and that's what the records end up being. And then the last one is the site data. We made an extra table to hold metadata for basically pits because we added it all into the layer data, and that metadata gets repeated for every record. It ended up being really burdensome. So we tried to separate it out and create some ways to map it. Okay. So there's some resources here. All of these are the libraries that we have built and built documentation for. If you go here, there's a ton of examples. You can scroll through. There's notes on what we've done with data. So some gotchas, what we did with S&P profiles. I try to include the NSIC links when we do this so that people can just bounce around however they want. I use it that way. Oops, I'm going to the NSIC. This documentation is a little bit behind because we made a bunch of edits in the database to make it a little more scalable. Last year, for those who remember, it was just limited to Grand Mesa. And this year, we kicked the door open and it's the whole West now. So we have UAVSAR data, the Boise River Basin, we've got the time series bits and whatnot. There's a lot of information here. You can solve a lot of your questions in here. But I'm also happy to go through it too. The rest of these links, the rest of these links are SnowEx PD. That's how we built the database. So if you're curious what the upload script looks like, maybe some of the metadata that we just locked in or hard coded, that can all be seen there. You can also see how we're testing the database. And then the rest of these are things you might want to look up if you're building queries to understand these errors. PostGIS is where we're pulling a lot of these functions to do these spatial things. And then GeoAlchemy is the geo portion of the Python SQL mapping. That makes sense. And then SQL Alchemy is the object relational mapping to the database that we're doing for just general Python. So if you have some general Python database questions, SQL Alchemy is the repo to go after. And then finally, this is, I think, probably the most used resource for me and I think most folks is the Hackweek database cheat sheet. This in here is just everything that I use a lot to do filtering and querying, kind of some general details with links to the API on how these are formed in the code. Some functions that you're going to use a lot, like this one is my favorite, query to GeoPandas. You build a query and it dumps into a data frame that you can plot right away. That's pretty cool. Here's some useful PostGIS tools, which are linked back to the original documentation too. Again, we'll go over this in a little more detail, but this is kind of, I would expect, the space you'll be using the most. All right. So at this point, I hope you know what tables matter and which one there doesn't matter at all, at least to you. And then what columns, or at least how to get at some of the column names that you want to work with. And then these resources that you can come back to and click on. At this point, are there any questions about how the database is structured, or where I can find certain information about the database, or when can I buy a MICA here so that you can help me form query? None? Okay. All right. We're going to get into the best part, not the best part. MICA's part. Prime's part is the best part, but this is what's necessary for the best part. Everybody here is going to want to build a query and they're going to want to filter on stuff. And filtering is going to help you prevent yourself from downloading gigs and gigs and gigs of data and waiting hours to find out that you just downloaded the database. So right away here, you can use your cheat sheet. I would just keep that up because we're going to have a little exercise here at the end where you're going to tweak some stuff. To get started here, we're going to import our database function. We're going to form that string again. And these are lines we're going to need for every query. We're going to execute that. I'm going to import all of the tables. Now here's where the kind of rubber meets the road here. We have this function that we can get from the session object called query. And this is where we're going to be able to start building any kind of query we want. And it starts with pointing to a type of data, and specifically a table, right? In this case, we're going to execute a little query on the points table, the point data table. We're just going to limit it to one record, which is not super useful for science, but it's a nice way to protect yourself from downloading a million GPR points, which does exist in the database. So if you execute this, you'll find you get back, I guess it's printed already. But you get back this list of result, and it's this thing in memory, right? Does anybody remember what this thing is? We talked about it a little bit in the ORM part, what these objects are, right? What did we just get back? What does it represent in the database? A single point, right? And how is this object useful to us? Are we able to use it in any way, and how do we use it? That's rapid fire. Feel free to just throw out your answers. What if I wanted the value from this record? How would I get at it with this result? Which is a column in the table. Okay, so this is what I'm concerned about, because I think people glaze over when they say ORM, right? And that's totally expected. I glaze over when I'm talking about ORM. But what you do here is you just got back a single row in the points data table, right? And each of those columns now are attributes to that object. So if I want any column piece in that single row, now I can take this object and go dot value. Now I have a casted number I can use, right? An integer or whatever it ends up being in this case. We don't really know. And we can figure out what data it is. It's a type, and it would give back, oh, it's a GPR point tape, or whatever. So what would you expect if we changed what's inside the limit, right? So up here, we have this limit function, and I said limit 1. If we did 100, what would you expect to come back in this list down here? 100 points, right? We get back 100 point data objects that we can then begin to parse and do stuff with. So this is a super limited example, no pun intended. And you're pretty much never going to do that unless you're trying to protect yourself from a big query, which is a useful tool, but it's not useful for your work. So what I like to do is I carry a limit around when I'm building queries, and at the very end, you should never end with a completed query that's got a limit in it. So once you've developed it and you've got it to the right data set that you want, take that limit off there and make sure it's by itself. Because the limit is just giving it to you based off of the unique identifier. So it's not a useful science tool. What is useful for science is filtering, right? And the cool thing about these filters is we can kind of chain them and build them along. So right here, we're going to execute this block of code. You're going to get your engine and your session object in. I like to bracket my codes blocks with the it DB and the session object close as closely as I can, right? Because what happens is if you do it at the beginning and the end of your hub notebook, at some point, if you're like me, you work for 4 hours in this block, and you've got code up here that's holding stuff in there. At some point, the database is going to go, you haven't done it in a long time, and it kills your connection. And so then you got to rerun it. So I try to bracket my data collections as closely as I can. And that's totally fine to have a bunch of them, right? So get session, close it, get a session, close it, or whatever, right? So here we get our session. We're going to form a query on the layer data table. So these are any of the PIT profiles or SMG data. And right away, I'm going to filter on density. And so I'm going to get a density, I'm going to attempt to get a density profile, but I'm just going to limit it to 5. Again, to protect myself, because there's a lot of PITs. Something like 600 something between the two of them. For that numbers. Don't quote me on that. You execute this. Again, you get back a list of layer data objects. And these have all those attributes we can get at, right? So you can figure out what depth this layer was at. I think some of them have the observer names in it, which makes for an interesting game. You can get out the different samples that were taken at that layer. You know, some of these density profiles have 3 samples for each one. So you might be thinking, I want to filter more than just the density. I do too. And what's cool is you can continue to change these filters here. And you can just use a different attribute or a different column in the database to filter on, right? So right away, what we could do, and I encourage you to try this along with me, copy this line, paste it right below it, and we're going to say site name. We're going to change this to brand in capital letters here. And right now, what this is going to do is it's going to limit us to all the density profiles that were collected at Grand Vista, which now spans multiple years, but we can play some games, right? You execute this, we get back the same result, but it's again these layer objects. Okay? Now you might be thinking, well, I don't really want all of the columns. In fact, I really only care about the density value, or I only care about maybe the location that all the density profiles are taken at, right? I'm just going to build a map. What we can also do is in this query object here, this query function, is change this to an attribute we want to get. And the important thing to remember is that whatever you want back at the end of the day, when you finish filtering, this is what you're going to get back. So whatever's inside the query parentheses, that's what you're getting. So here I'm going to do dot value just for kicks. If we do this, now we actually get things we can use. And they're in this kind of funny space. It's a tuple. And that's because you can add more things in there. So maybe I want layer data dot value, and I want layer data dot site ID. I want to see the unique site IDs for these, right? Now I can see here's a layer and a site, and you can chain these together however you want. Again, we're still limiting here, but you can open this up. The more filtering you do, the less worried you have to be about the limit. Okay. So if you're like me, you're like, well, this is great, but I don't know the density is spelled that way in there. I don't know that Grand Base is capitalized or whatever. So how do I find the exact match for what I'm trying to get at? And the key and probably the most useful tool for you is distinct, which just tells you the unique, whatever you're asking for in the database. And there's a whole bunch of examples of that. We're going to execute those. Again, we're grabbing our session object. I'm going to query the layer data table here. I'm asking for types. So we're going to see like density and hardness, things like that. I'm asking for the distinct version of all of those. And then I'm going to execute it and give it a little nice print, right? We're going to do this for a bunch of things. These are all things that I do frequently to figure out how to filter. Try to break the database. Be fun. And right away you can see we can see who some of the observers were. We can see what kind of data sets are in there, like the grain type or the temperature. Megan did that really cool temperature profile evolution of pit sites. That was, to me, that was really neat. You can see what kind of instruments are being used in there. The available dates, which is probably the most important, one of the most important ones you guys may be interested in. So I encourage you at this point to maybe comment out some of these and start to change the table and maybe an attribute that you're interested in looking at, right? So some examples might be site ID. Maybe you're interested in some sites, or maybe you're interested in where what GPRs were used. So you can do point data dot instruments dot distinct. I'd encourage you to try to tweak this a little bit and execute it right now, and just maybe confirm to yourself that you understand where this is heading. I think I'll try raster, or image data dot observers. I'm curious who took raster data in the database. Make it rid of all these kits. Yeah, so in the raster data, I can see we've got a USGS observer, the UAV SAR team, and we have ASME, right? And this also works with filtering. So you can continue to filter, chain together those filters, and then do a distinct just to see what options you have. Say at Grand Mesa between these dates, did anybody collect density or what? So that was kind of a really rapid fire exposure of how to do filtering, and that we can continue to change those filters I don't know if I pointed that out super clearly, but here we're just collecting this query object and then filtering on it again, right? So I formed it first here using the query function, and then I did query.filter, and this can go on for as long as you want. And then at some point you query.all to execute. So hopefully you have a sense for how to build some queries that way, and then specifically how to maybe isolate some column data in your query, right? By doing the point data.value, how do I get a value instead of that object that's very foreign if I print it out. And then maybe even you have an idea of how to determine what values of things you want to filter on, right? By using that distinct function. So we're going to stop right here for a second. You can raise both your hands. Really out loud. Just to stretch. Yeah, come on, you can do it. There we go. And then you put your hands down. Are there any questions? Filtering. Yeah.
So once we go like as far as the values that we're looking for, are you like the interactive that is beyond this query, like query? So are you like
Yes. Yeah, and I think this something I kind of skipped over is that these are, for the most part, there's one exception. These are all in the right text, right? So if you open some CSV or whatever text file, you have to cast everything. This is all being done behind the scenes for you. And so you're getting stuff in integers, you're getting stuff in strings or whatever. But yeah, the question was, once I form my query and I execute it, are there tools or what do I do after that? Yeah, there are some tools in SnowEx SQL that you can use that allow you to dump into a data frame, and then you're off to the normal data science process.
We'll go.
Yeah, we're going to go over that too. Some of these things are kind of a chicken and the egg deal, and we just pick one. We could have rearranged this and it still probably won't work. Are there any other questions? Cool. Well, at this point, I'm going to expose you guys to some prime time, and I'm going to sit back for a little.
Mic as high as possible. I got a plug in. All right, is that okay? Likewise, good. Well, thank you, Micah. Basically, just to go into more of that question that was just asked, I'm going to go through some more complicated examples, kind of turn the hose full blast here. And so I want to reiterate, if you don't get this, totally expected. This is kind of just giving you like a bunch of pre-answered Stack Overflow questions you can come back to time and time again, so you don't have to necessarily ask everything. Also, the cheat sheet that Micah brought up, super valuable. I did not write the database. I am not as familiar with it as he is, so I go back to that pretty much every time I'm going to get on the database. But our first example will be visualizing depths. So I already forgot the number. I think it was 37,000 manual snow depths in this, just Grand Mesa. Just in Grand Mesa. So that's really cool. I don't know what to do with 37,000 snow depths. So how do we get maybe to a subset that we want to look at, and then how do we get that into the data frame? How do we find it? And that's what I'm going to go through here. This is not like. Step one will be connecting to the database that will start to look familiar now. Step two is we're going to use that filtering that we just learned about and sort of filter down to maybe something we can use. And then step three, convert to a geodata frame and fly. So get connected. We'll go through this real quick. Get DB function. You've seen that a few times now. Depth data is a form of point data, right? Single measurement, one place, not a vertical profile to it at all. Not really with spatial, so it's point data. This is the first time we've seen this query to GeoPandas, so that lives in the conversions module. Actually, Megan showed the query to GeoPandas. First time today we've seen it. So you got to get that, and then We'll import this date module from date time because we're going to do some filtering on date. So let's get that run if you're following along. And then we'll start to build this query. So like I said, we're interested in depth data. So we're going to specify our data set as depth. Our collection date, we saw this using the distinct function from the last tutorial. So we know that there is February 7th, 2020 depth measurement in there, at least one. Our site name is Grand Mesa. Like I said, 37,000 that's at Grand Mesa. We'll get the database and then we'll start to build the query here. We're starting with point data. We just want the whole object back for this example. We're going to filter here to our site name is Grand Mesa. Our data set type is depth here, and then we'll filter on date, which is pretty slick. We'll limit to 200 because we're kind of just exploring again. I don't really want to bring on everything from that date. And then instead of calling all like we did before and getting that list of our objects back, we're just going to pass this raw query into the query to GeoPandas function, and then pass along that engine that came back with the function as well. That'll give us the data frame back. And then here we'll print out the length of that data frame. I think we can guess how many depths we're going to get back if we put a limit on there, but we'll see. And then we'll close up that section up there. So everybody should be able to run that. And we'll see 200 records there. Not a big surprise. Kind of cool. Now, if we want to plot that, so we want to actually do something with the data more than just read about it. We have the data frame, and GeoPandas is the georeference form of pandas, if you're familiar with that. And it comes with a lot of plotting functionality. Pandas does too. GeoPandas can do maps. We're going to plot the value column. That's where our value of interest is stored. We'll give the legend, pick a color map. This is some formatting stuff that we can go into if you have questions. I'm going to skip it for now, just interested in talking about data and then go over this. Now, it doesn't look very good. We grabbed 200 depths. They are kind of all over the place, it looks like. So this is going to be a common thing that happens to you. We filtered or we limited to 200. It's not really what we want. So what do we do to get down to more of the data set we want? And that's where this is going to come into play. So if we just wanted to get a depth spiral, we could probably think about what instrument was used to collect the depth spiral and add a filter onto our previous query to get down to maybe one depth spiral. For that, if we want to know all the instruments, we're going to run that distinct again. Cool. A lot of people are running stuff, so that's good. And we can see all the instruments that we have depth measurements from. So I'd like to take a minute and invite everybody to go back up to that previous query and to duplicate the previous.
I have a question, comment.
Yeah. Yeah.
So because we're only selecting depth data sets, and it looks like I retrieved some GPR depths because it's a really smooth plot. Alicia looks like she got probe depths.
Yep.
So I guess my question and concern is how is it deciding which 200 depths it's getting?
Yeah, and that's the problem with the limit is that you're not necessarily going to get the same results back. It's really how we built the query, and it went through, selecting this site name. I gave it a data set back, and then selected down to, the date, and that gave it the data set back. And so you're not going to get consistent results necessarily unless you build a query that will give you. I mean, you always get the same data. You don't put a limit on it. It might not be in the same order. So we can add more filters to get us down to the same data set. But I wouldn't assume that the index that it came back in is, I should have repeated the question. We're getting consistent results the more that we run this. So how do we get to a more consistent data set? And that's where we put more filters on it and don't rely on limits, except for exploiting the data. So that's what we should all do now, though. Let's take a couple minutes and let's try to limit to not use our data. So we want a depth spiral. Let's go look at our instruments that we could maybe limit on or filter on to get just a depth spiral. Does anyone know what that data was, what instrument was used to collect those? Yeah. So we can filter to the magnet probe, add another filter onto this filter chain up here, and then try rerunning that code block again. And mhm. Yeah, that's a great way to explore it. So the question was, could we use the count function on the end of the security to what? Yeah, it is. So there's a count function. I'm not sure. We'll use that in the next example for sure. But could we explore the data? Maybe not return everything, but just say if I ran this query, how many rows would I actually get back? How many rows in the database match this query that I'm about to send over? And that's a great way to do it. You can use count instead of the .all, or if we wanted, I could just, we'll run through that real quick. Let's, so if we just did query count. Oh, database is working hard. I got it. Okay. Okay, so if we had run this and not limited it, we would have gotten all the deaths at Grand Mesa for that day, which was apparently 38,000. I'm now wondering how I said 37,000. Oh, because we're not just talking names. Right now we're talking everything in the point data that was collected on that day. There's 38,000 points. We would have gotten 38,000 points back. That would have been a lot. Yeah, that is a good distinction. Probably depends. So what is a lot is the question. It does really depend on the data set. 38,000 rasters would be a lot more than 38,000 points. I don't really have a great distinction for that. 38,000 points, you totally could do an analysis on 38,000 points. Probably wouldn't be that much data compared to trying to do it on 38,000 rasters or something like that. There could be, if we're doing an analysis of spatial variation in Grand Mesa, you might want all 37,000 manual depth estimates. It really is dependent on your end goal. Yeah, the database could definitely, it could return all these, and that would not be a just problem. Yeah, if we all executed it, it would I think it would do it, but it would take a while. Yeah. So the question is, how do we get the snow depth time series instead of just one day? If we didn't build it on the date here, it would return everything. So if we let's say we just build it on instrument and site name, then it would return all the dates, and we could use that to order by the into a geodata frame, order by the date, and get a metric plot. It would be a little weird if we built it spatially, but yeah, we can get all the time series if we don't filter on that. Okay. Was anyone able to successfully filter down to maybe something that looks like a depth spiral? Cool. So I'll run through that real quick, but break back down too badly. This is the limit. 100. And then what we did here was, or what I want to do is query.filter, my data.instrument. Spell everything right. Let's see, we still get 200 records because I limited that, and then okay, so that looks a little bit nicer. Looks a little bit more like what we expect. We're now filtered down to pretty much one depth spiral, at least 200 points out of that spiral in Grand Mesa on February 2nd. To recap, we're learning more about queries, changing these filtering or these filters to get down to data sets we want, and hopefully we know where to find the queries geocanvas function, because that is used all the time. Are there any questions at this point? Yeah.
It's not that that's clear, but, I'm looking for that, second, close being used here and whether, like, context or variables persist through after.
Okay, so the question is, how is session close being used here, and do objects, variables, all that jazz persist between the different code blocks? Yes, to the latter, objects do persist. We actually don't need to close the session here. That's probably just a typo. So because we close the session, you only need to close the session once after opening it. This is a legacy from probably not having closed in this previous code block. But yeah, I like to do open a session in a code block and then close it near the end of that code block and then just continue to do that. But you could leave it open between code blocks. It will time out on you at some point. If you
But after you close it, like that thing is still persisting in the node.
Yep, it's just a close, like the object's still there, it's just a closed session object. So you couldn't query it. It would yell at you. Yeah.
If you had finished your query and you know,
Yeah. Yeah, so the question is, if we put everything into a pandas data frame, could we continue to work with that for as long as we have this Jupyter notebook open? And the answer is yes. Any other questions? Yeah, the question is, will the Snark database be available after the hack week? The goal is that it's available for the foreseeable future. We would like to be available forever. There could be more, I'm not gonna say restricted. We might ask for your IP address. We're still trying to figure out the correct way to make sure that we understand how many people are using it. And that's kind of the tricky thing. So there might be a hoop or two to jump through, but it will be available. So there's been a lot of promises around some cool GIS functionality, and we're going to go through that now. This is a complicated, same disclaimer. Basically, I have to go back to the cheat sheet for this all the time, but there are some really cool operations you can do to figure out how to use these data sets together. And that's really the power of the database. Like we said, you got point data, you got raster data, you got layer data. There's all these diverse data sets in here, and it's not necessarily straightforward to learn how to use them all. If I want to find all the points near another point, how do I do that? If I want to find all the rasters that maybe I can compare to this point, how do I do that? That's not straightforward, but this gets us a lot closer. So we're going to run through some of these functions and give you the resources to continue to explore them. A few things to keep in mind. A lot of these functions are going to start with st underscore some function name. That's sort of the naming convention that PostGIS has for all of these. And then we're generally going to classify them into stuff that has to do with points and stuff that has to do with rasters. It's a good way to keep them separated in your mind, although that's not a hard task to do. So we'll run this first code block again, import some stuff, name our database, or construct that string rather. And then we'll look at what if we just wanted to get one tile of a raster in the database. So I think this is the first time we've played with rasters in the database. One thing to keep in mind, they are in well-known binary format, which I don't personally know how to use. So we're going to learn how to get that out of the database into a usable format. If we run this second code block here, we will see what are we doing here. We're getting the database. We are interested in the raster attribute of image data. So rasters live in image data. Good thing to keep in mind. We're going to limit to one of them, and then we're going to run that query. And we'll print out basically the first object that we get back from that query. The only object we get back from that query because we're limited to one. And we'll see this. This is where we're getting back. So kind of like what we saw in some previous examples, this is an object. Cool. I don't really know what to do with that, but it's there. So now we'll learn how to actually do something with it. We're going to start to import some useful functionality from SQL alchemy.sql. There's a module called func. It has a lot of functions. There's in versions similar to query to GeoPandas, we have this raster to raster.io. Similar idea, we'll show you how to use that here. And then raster.io, if you're not familiar with raster.io, it's a really common Python package for reading, writing TIFFs, and other geospatial formats. And it has some plotting functionality too. So we're going to bring in this show map. And then we're going to make a pretty complicated query, and it's going to give us the first tile of a raster from the database. So one thing to keep in mind is that the rasters aren't just stored as like a block in the database. We store the rasters actually in Amazon S3, and then they're tiled so that we can, if we are interested in comparing maybe to, one point, we don't have to pull down like a 2 gig raster or something to do that. We can pull down, this little chunk of raster that has to do with the point we're interested in. But that does mean that you need to keep in mind that things are tiled and not just expect to get all the data.
Say you want to plot all files at once, do the whole raster, is there a certain query you would write for that, or is that a little tricky because it's tiled, or?
Yeah, so if we wanted to plot the whole raster, how would we do that? And that's the next. We'll show you at least how to get the chunk that you're interested in. So more of the raster, you could get it all this way too. I'm also just getting ahead of myself, but yeah. So in this query, we're going to use this func.sts on the raster attribute of the image data table. That goes inside of our query. So we're sort of building a transform that lives inside of the query. So we're not just grabbing that attribute, we're grabbing some transformation on that attribute. And that's what lives in that query part of the function. And then for this example, we'll filter to depth data and then limit 1, and we'll run that query. That will get passed to the raster to raster.io function, along with our session object, the session, then that query. And then that returns the list. So we'll grab the first element of that list and plot it, and then kind of close our chapter. So there you go. We got a plot of depth data. I don't particularly know what you can import it, so I have to, but we have a plot of some depth data. Okay, we're about to get to unioning, which is putting multiple files together. So any questions before I go on to that? The question was, are we just pulling separated file? Okay, so we're going to go through 2 different things that I imagine a lot of people would use, and that's ST-union and ST-intersex. And we're going to do that by comparing a tile or however many tiles are relevant to us, some raster data to a pit. So here in this code block, we're going to import our site data. Site data, Michael went through that earlier, but that's the description of pretty much all the sites that we have. So like every pit has an entry in site data. We're going to import this type from GeoAlchemy2. This is why we build examples, because I wouldn't know where to find it. But now we know that we have this raster type living in GeoAlchemy2. And then similar to that func module we brought in earlier, we have the dfunc module from GeoAlchemy2 functions. So we get our database. This is our site that we would have seen from the site IDs earlier. And then we'll start building a query to get some info about that space. Here we're going to grab our geometry object of our site data. So geospatial reference basically of our pit. We're going to filter to the site ID that we want. Grab a distinct on that because we just want one location, and we'll get our first record that's drawn back there. So that'll give us some description of where our page actually is. Then we're going to start building the transform that I just talked about, where we build some transforms on the data we're going to get back, and that lives in our query. So our transform here, we're going to tell the database that we want to union our rasters together when we get those back, and those rasters are rasters. So that lives in the type here. We're then going to also say that we want that not as just a well-known binary. We're going to get this something we can use, pass it through SDI div. And then this base object that we just built will live inside our query. So this is something that I can see people doing a lot. That's why we give you these lines of code, because I'm not gonna be able to write this from memory. I'm gonna go to this example. I'm gonna grab this and say, I know I want some union rasters in this query. So we'll throw that into our query. We'll filter to some inside data. We will then chain a filter, and we want only this polarization of the real data. Then we're going to have one more filter, which is the SD intersex that we talked about. And so we only want the rasters that intersect this point that is the pit. So we only want the rasters that are going to overlay onto the pit that we care about. Then here's our readout count. Thank you, Megan. That's a great way to explore data. And then we'll run that query and pass it to the raster IO function again. And then similar to the last example, we'll plot that up. We can run this whole thing. We'll get some fun deprecation warnings. And don't worry about those. And plot over. So this is our raster data, our union raster data that is related to the pit that we're interested in. One thing to note here, we printed the count. The count is 1. Because we union the rasters, the count should always be 1 because we're really only getting one thing back. We said there might be a bunch of tiles here, but we want those all together, so we're only going to get one object back. Okay, that was a lot. So we should review a little bit here. Some things to talk about. I don't know if we just want to do this as like an open forum kind of thing. What's the difference between union and an intersex? Did you notice that we grabbed the SD union from the G funk and not our SQL from the top funk? And how many SD unions are there actually? I will put the first one up if anyone wants to answer that. Did you notice what the difference between a union and an intersection is?
The union brought all the tiles together, but the intersection kind of then refined that, I guess, further.
Yeah, so the answer was the union brought all the tiles together, the intersection refined our query, and that's exactly right. The union all the tiles, and the intersection, we said we want the tiles to intersect this exact spatial description, which in this case was. I'm not going to ask for the how many SD unions and all that. So we should go through these really quick. This is an SD union that relates to rasters, which is the one that we brought in GFUNC, and then there's an SD union that relates to geometry, points, that kind of thing. The important thing to remember about this GFUNC SD union is that we passed it this type of raster because it needs a reminder that hey, this is raster data. This is the exact type of raster.
The G-Bump is for the music of raster.
Yeah, G-Bump raster. That's the important thing. Any other questions? Next. So the question is, do we set a distance anywhere? And no, we didn't. It's pretty much, does this tile contain this point? But the distance is a great segue for the next example. Yeah, it's very thorough. Any other questions? Okay, so next question. What if I don't care about masters? I just want to know, I still care a lot about this pit, or a pit at least, and I want to know what other data I can kind of compare to my pit data. And so we're going to introduce a function called STBuffer here and learn how to collect all the points that are within the distance of our pit location. We're going to import point data because I no longer care about rasters. We're going to import our query to GeoPandas again and some plotting functionality from platform. Different site here, but another one of those site IDs we would have seen in that unique list of site IDs. And then we're going to set a buffer distance. In this case, we're going to say, I want all the points within 50 meters of my pit. Megan. Okay. That's a good point. So these side IDs aren't just random, like collection of strings and numbers. They do have some representation. I can hopefully repeat that. The one that was in shallow sound, and it was in the north line. Okay, is the three? And that's the three. Three means fearless there? Or not?
Three is the third.
Oh, the third iteration. Okay. Okay, so it's in a relatively, you said 3 year old. Okay, so it's one is a shallow open area pit on the north line. Okay, and it was the third iteration, right?
The third
Progression. Yeah. Okay. That is a really good point. Site IDs do mean something, which is nice. It's better than just assigning random numbers. Okay, so 50 meters is our buffer distance that we care about. We're going to get our database and we'll start building the query. Again, this is to get some description of where the pit is located. So we'll grab that geometry object and we'll filter to the site we want. We're going to both store this as a GeoCanvas array because we want to do some plotting with it. I don't want to rewrite plotting from scratch. And then we're going to get, this is similar to what we did in the last example, we'll get some description of the geometry that we can use in queries. We will then start building a description of the buffer. So here we're going to query using this SD buffer function, and we'll pass in that geometry and our distance. And now then we'll run that, grab our first element again. And now we have something that we can filter on that represents this 50-meter circle around our pit. So we'll build another query, this time on the point data. We want to get all the point data back. We'll filter to just depth data. We'll filter to some instruments that we're interested in. So this is manual depth instruments. And then we will change another filter on here to filter to just the geometry that is within, or rather just the point data that has geometry that's within this buffer. Okay, and that's the ST function. Throw that to GeoPandas and then build a cool plot out of it. So hopefully what we'll see out of this plot is we'll see some representations of points, and we will see some location of where the pit is every triangle. Sure enough, we have some depth measurements, all the depth measurements that land at 50 meters of this nice little green triangle here. Okay, so recap, there's a lot of PostGIS functionality. Go slow with it, ask a lot of questions, look at these examples, look at the cheat sheet, but hopefully you know where to find the functions. What geology 2 is now, or C block me, although that is still what we need to. And how to chain these commands together in a way that might get you some data that you want. So I think that's a great place to stop for questions again. Any questions?
Yeah, so this is really the term that you want to use. I guess I'm still struggling with forming queries on these. So we're going through and you're saying query, the section query, data, depth, and then you're saying instrument, fitting it, header, names, macro. So I've been trying to form a query to say what are all the instruments, and there is one. Or that's the
Yeah.
So how did you find out what?
Yeah. Well, no. So the question is, yeah, basically the syntax is very complicated, which is where would we find all, like how could we maybe get all the instruments? For instance, in this example, I totally skipped over this. We use this this filter point data instrument in with this nice little underscore after it, and then we give it a list of what instruments we want to filter to. So instead of saying filter equal, micro, I now want micro and Mesa. So how would I maybe get them this? And I think, so in slide 4, we have all, here we're driving query instruments that are related to depth, and we're doing a distinct list of all of these. So that one. Probably, yeah, let's just grab.
No, that's awesome.
Yeah, but yeah, so I know it's kind of hidden. I bet I would wait to have this in cheat sheet too. Do something very similar. Any other questions?
We wanted to look at two snow. I mean, maybe there's other ways to do that. Could you just put in another site ID next to it, or where it doesn't have the site ID, it might not.
Yeah, so what if we wanted to look at two sided or not sided pit at the same time, right? Did you want one or do you want block two? Let's see, let's test it. How you go to okay, I'll just start. So let's grab some layer data. I'm just gonna Mesa like all this. And let's build a query that just limits where. What? Oh, let's grab all those sites. So we had and let's do a couple. So we're gonna filter on layer data, that site for density and Mesa. Limit 2 there. So let's find a couple of site IDs. So here's a couple site ID out. Great, we should do distinct. There we go. It did. Okay, so here's a couple site IDs. What if we want to filter to those? So layer. So this is a great example. I'm just going to go steal this logic from this example that we just looked at. Site in 1. Full layer there back. So not great spelling. Query and now we can print the result. We'll run it really quick to see what that looks like. And then I can't type it without a hit ID. So here's a nice little representation of the data frame that we get back. And then we're just going to do a result plot. This isn't going to be a pretty plot, but it will be a plot. Okay, so it's the same thing pretty much because it's a progression. So if we zoom in, Doesn't say that, but. Answer the question. How would I talk to this?
So pretty much when we're in the GPR or the last line, we pretty much not letting people and then do our intersection.
The question is, how do we do this? If basically we have two spatial data sets we want to find out where they overlap. Yeah. I don't have a great, there is functionality to do it, and we could probably work up an example. I don't have one.
You can build, so you can get all the LiDAR data, and you can build an envelope. LiDAR data meets your requirements, and you can say, I want to know all the GPR points that fall in this.
So the answer from voting like it is, we could build an envelope out of one of the data sets. So basically do a description of our bounds and then filter the other data set to everything that lands in that envelope. And there's an SD envelope function. I'm not going to do that on the fly, because it's take a flag. Someone else there? If you want to look at, I'm not going to go through this one, but there are really easy ways to export data. So say I got a data frame back, and I want to store it as a CSV, or I want to make a shapefile from this data frame. There's literally two CSV, two files that will do that for you. And there's simple examples in here. Same with rasters. Dump it really quickly to a local TIFF if you want to maybe work offline or something like that. And then I don't think I'm going to go through this one either, but there is a bonus challenge if you want to get really familiar with bit data and how we might make a density profile. It is not pre-filled out. There are some helpful blocks of code of how you might start to filter the data. I'll just preemptively give everyone an A because I'm not going to check your work, but this is some good homework. If you want the solution, you can Google this in GitHub. Go on GitHub. There's a solution in here for you. And I can also link to that in the database. So I think I'm going to pass it back to Subnaught here to give us a little wrap up.
I almost went down there. Been fun. We went for a jog this morning and I tripped and fell in the parking lot in front of a car. It's a road crash. Okay. So I mentioned earlier that there are some ways to look at this in QGIS or ArcGIS. Again, for the time's sake, there's an example on how to do that. Click here on this link. And go see. I did how to bring in the GPR data, and I did some clever skipping of points so that it's not the whole data set. Similarly, I did an example of ASO and putting pins over the top of that. There's a lot of things you can do there. There you do have to know a little bit of SQL to get by, but it's not bad. I was able to cobble together stuff that made sense to me. Yeah, so I guess I hope at this point we at least convince you that there's something really valuable in this thing that we're calling the SnowEx database. And I'm sure it's feeling a little intimidating and maybe full of barriers to get at. My hope is that you guys have all seen something in here that's of interest to you. There's a data set, and there's some filtering tools that you think you could probably put your hands on by going back. That's kind of like my minimum threshold of this hour-and-a-half conversation. We're going to be around, and I'm really excited to work up queries with anybody who wants help with that. We have a database channel on Slack, so if you don't want to talk to me in person, because maybe I put on deodorant this morning, you can just say, hey, Micah, I have questions. And then, hey, Micah, we'll get back to you. It is open source software. And this is a cool thing for this group of people because there's a lot of very capable Python developers and people who know a lot about other components of SnowEx data. So even if you're not, say, a capable Python person, you're not going to get in there and improve SnowEx SQL. Let's say you form a query and you're like, no, I'm pretty sure that I was there at this bit. My name's not listed. You can make an issue on the SnowEx DB page and say, hey, Subnaught, you screwed the pooch on this one. Can you give it a fix? And we can go and begin to work on that fix and update. That's kind of the cool thing about the databases. We can be changing things in a way that goes more towards what the correct representation of it would be. And we can track all those things. And that's a great way to contribute. You might also have a data set that you're really interested in that's not in the database yet. And there's a lot of them. And I'm like slowly ticking off the list. But if there's something in particular that you want to work with, even during Hack Week, we could try to work it in soon. So I'm not going to promise we will get it, because some of them need a little more work. But there's a lot of things, like all the GPR data sets now just flow into the database. I just literally need to do it. So you can participate in these things too, even if you're not super database person or super Python person. There's also examples you could work on. There's plenty of typos that you'll find looking for those. And I would strongly encourage you to partake in this community software that way. Outside of that, all this, like you can pip install SnowEx SQL, so even after, months after Hack Week is over and the Jupyter Hub is down, you can just pip install this and start working with some a little bit too. So it's not going away. To that end though, HP is funding all this, and so if you get a chance, you should tell him thank you, because he asked me to do it 2 years ago and paid to do that, and then continues to pay to keep it alive. One of our goals is to kind of cobble together enough support for folks that would secure long-term funding. So certainly think about how you can interact with the database and publish about it, especially using the Intersex published data sets that are in there, and be able to begin to point that we do need this, I think, and hopefully you do at this point, but we do need this resource to access such a diverse data set, right? If we're going to really do some serious science with UAVSAR, and I don't mean serious as like slide, but serious, you're going to do science, which is all science is serious. With UAVSAR and depths, you're going to need tools to connect those pieces. We've done a lot of work for you already. Yeah, I would say give thanks to HP, and if you can find him, he's off the field, so maybe just volunteer and bring beer. How anyways, that's all we have on the database. We're happy to help anybody who has questions or wants to do a session with me. Maybe do a session at some point. There's enough interest. Thanks for listening.
The plan is to get as much of the data in the database, and if we move with SnowEx to Alaska, continue this kind of effort, things might change some, but I think that's definitely worthwhile investing your time in so that we can continue to use it. And I think the more people we can show that are using it, the easier it's going to be to keep advancing it.
Thanks, guys. We'll now head off for lunch. So we're right on schedule. We'll come back in an hour, 12:45. So Jen had indicated that we would have someone here to watch our stuff. No answer, great. So we're going to be in the room. Feel free to leave your computers. You don't have to lug them around. We ensure that everything will be secure. Have a good lunch. We'll see you in an hour.